Welcome. Today we're going to cover rotational kinematics. Kinematics was the first topic we started in the beginning of the year. I gave you three formulas which I referred to as the kinematics big three. Those three formulas were this: x final equals x initial plus v initial t plus 1/2 at squared. X is our position, x final is our final position, x naught is our initial position, v is our velocity, t is how long we've been moving, and a is acceleration. Where I am is where I was, plus how far I went because I was moving, plus how much further I went because I was accelerating. The rotational kinematics version of this, instead of using x, instead of using something like meters or inches or miles for position, we're going to use angles. And the letter we're going to use for angles is the Greek letter theta. We could also use the Greek letter phi in the event that there's more than one angle in a problem, but right now let's stay with theta. So our first formula is going to become theta final equals theta initial plus, now instead of v for velocity or speed, we're going to use angular velocity, and the letter we use there is the Greek letter lowercase omega. Initial. Time, we don't mess with time. T is time. Plus 1/2, and the letter that we're going to use for angular acceleration is alpha. T remains t squared. The second formula we had was that a change in speed equaled acceleration times time. And our angular version of this is going to be lowercase omega equals alpha times time. And finally we had v final squared equals v initial squared plus 2ad, and that's going to become omega final squared equals omega initial squared plus 2 alpha theta. Let's talk about the units that we're going to use for angles. The most common unit that's used in everyday life is degrees. For example, 90 degrees makes a right angle. The one that we're going to use most often in physics is the radian. There's two others, rotations and revolutions. Rotations and revolutions are often used interchangeably. Technically, the difference between them is that a rotation is something that spins on its own axis. For example, the Earth spins on its own axis once a day. It makes one rotation a day. And revolution is when one object goes around another object. For example, Earth goes around the Sun in 365 days. A revolution is 365 days. But often these terms are used interchangeably. So for example, you've seen the term RPM, revolutions per minute. The old LP records that we used to use, or still do use, are measured in RPMs. The big ones are 33 1/3 RPMs, revolutions per minute, even though they're going around their own axis. The way I just defined it to you, it should be rotations per minute, but nobody says it that way. A degree is very small. There are 360 degrees in a full circle, or 360 degrees per rotation, or 360 degrees per revolution. A radian is much larger than a degree. Imagine you took the radius of a circle and wrapped it around the circumference. That's 1 radian. It looks like a large slice of pizza. 2 radians, 3 radians, and it takes a little bit more to get to 180 degrees, and that's pi radians, 3.14 radians. And of course, a full circle is 2 pi radians. Imagine we have a circle with the radius 30 centimeters. If we took a line equal in length to its radius and wrapped it around the circumference of the circle, we'd have an arc length of 30 centimeters and an angle of 1 radian. If we continued and wrapped another arc length equal to the radius, we'd now have an arc length of 60 centimeters and an angle of 2 radians. Continuing and adding another arc length equal to the radius, we now have an arc length of 90 centimeters and an angle of 3 radians. If you'll notice, it's not quite half the circle. To make it halfway around the circle, we'll need about 94.25 centimeters of arc length and a little more than 3 radians. We're going to need pi radians, about 3.14. To make it all the way around the circle, we're going to need to wrap the circumference with 2 times pi radii, which we call 2 pi radians. That will give us an arc length of about 188.5 centimeters. So a radian is defined as the ratio of arc length to radius. Since both arc length and radius are expressed in units of distance, in our case centimeters, we have centimeters over centimeters, which of course cancel each other out. And simply equal 1. Therefore, the radian is a dimensionless unit. You're going to see problems where we solve our problem, and at the end of the problem, the radians just magically disappear, and this is why. If we'd like to convert between our new angular values and our more familiar linear values, the conversions are this. Distance equals r times theta. For example, if we had a wheel of radius r and we rolled it through an angle theta in radians, our distance would be r theta. Likewise, our speed is going to be r omega, where omega is our angular speed. And finally, our acceleration is r alpha, where alpha is our angular acceleration.